this is question 6 from the 2021 MAT. Distinct numbers are arranged in an m by n rectangular table with m rows and n columns, so that in each row the numbers are in increasing order, left to right, and in each column the numbers are in increasing order, top to bottom. Right, such a table is called a sorted table, and each location of the table containing a number is called a cell. Two examples of sorted tables with 3 rows and 4 columns, thus 12 cells, are shown below. Right, so this is m rows, so that's m in that direction, and that's n for columns. And we're going low to high, left to right, and low to high, top to bottom. Right, we index the cells of the table with a pair of integers I, j. Top left corner being 1, 1. Okay, so that's 1, 1, and then we're going up from there. Right, so this doesn't look like a XY sort of thing. The bottom right corner being MN. Right, observe the smallest entry in the sorted table can only occur in cell 1, 1. Second smallest entry could be in 1, 2 or 2, 1. Okay, right. Need to keep an eye on these IJs and not think about them being X and Y coordinates because we're starting in the top left corner. Right, part 1, A. Assuming that m and n are both greater than or equal to 3, where in an m by n sorted table can the third smallest entry be? Right, well, let's just look in the pictures, first of all, where they've got them. So the third smallest one here is that one. The third smallest one here is that one. Right, so that's 2 options that we've got. So 1A. So we could have it in 1, 2. That's where the 12 is, which means we must be able to have it in 2, 1, because all of this is symmetrical. And then this one we've got in 3, 1, so we must be able to have it in 1, 3. And can we have it anywhere else? We can't move to the 4th column. So, I mean, there might not even be a 4th column, so we can't go there because that's at best the 4th one. Can we get to... No, we can't get to the 26 here. We can't get to that cell because that's got at least 3 things smaller than it. The one to the left, the one above it, and the one in the top corner. So it is just going to be those 4. We haven't got any other options. Right, part B. For any k greater than or equal to 4, satisfying m and n are greater than or equal to k, where in an m by n sorted table can the kth smallest entry appear? Right, okay. Right, let's try and think about... Let's draw out a little grid then. Try and think what's going on here. So slightly bigger table, what we got here, sort of 5 by 5. So say I pick out some cell, so say I pick this one here. What's the best that can be? Because that's what we want. What's the lowest possibility we've got for a cell? Because then that allows it to possibly be the kth entry. So in this case, this is, which way round was this? This is I. I is M, so that's our I, and that's our J. And if we're in this, we're bottom right corner of that rectangle. So we know that all of these, everything else in that rectangle has got to be smaller because it's left or above. Now it could be that there are other cells that are smaller as well, but that's the best we can do in this. The best that we can hope for that cell is that it's going to be that last one. It's going to be I times J is what we've got here, the I times jth smallest entry. So providing I times j is less than or equal to k, then it could possibly be where the kth smallest entry is. Justify your answer. Right, so the 4 cell IJ, the best case, so what do I mean by best case? So i.e. the well, the lowest k, was that what I'm looking for? The lowest k, or the lowest kth. Is that really a term? But anyway, so I probably know what I mean. So the lowest kth number that can be in that cell is IJ. Yeah, i.e. all lower numbers are in the rectangle with bottom right corner ij. There we go. Right, so that's done part I. Part II. Given an m by n sorted table, consider the problem of determining whether a particular number y appears in the table. Outline a procedure that inspects at most m plus n minus 1 cells and that correctly determines whether or not y appears in the table. Wow, this sounds tough. Briefly justify why your procedure terminates correctly in no more than m plus n minus 1 steps. Hint, as the first step, I'm glad I got a hint, consider inspecting the top right cell. Right, so let's think what we're going to do then. So before I write anything out, we start in the top right cell. What are we doing then? So if it is, actually I can write this out I think, so let's start top right. So we can then say if cell equals y, then, well, stop, we're done. Then stop, because we found it. Then we need to, so we're going to be scanning through the table. So we want to then go else if y is, well, if it's less than the value, so we want to go if it's less than the, well, wherever we are, so less than top right, well, let's say less than cell value, then we want to move, if it's less than, we're going to have to move left. Else if y is greater than cell, we want to move down. Okay, so we've shrunk the table then by doing that, because we've either removed a row or a column. Then we just repeat, I suppose, don't we? And then repeat. So we repeat this process. So, right, let's move over here. Then repeat until y found or reach bottom left cell. Okay, so that's the procedure. That's definitely going to work. We have to then briefly justify why it terminates in no more than m plus n minus 1 steps. Okay, so for that part then, we want to say, so each step removes one row or column until one row / column remains. So that means we're doing, well, we're taking off m rows and n columns, but we leave one left. Therefore, total possible steps equals m plus n minus 1, rows plus columns, but leave one left at the end. Right, okay, so that hint was very helpful. I think that would have been a struggle without the hint. Now, of course, you wouldn't necessarily have to start from top right. I mean, you could do the same thing from bottom left. That would do exactly the same. So we can't start in top left or bottom right because we wouldn't know which direction to move in. Now, if we start at bottom right and you say, okay, well, it's lower, well, which way do we go? Do we go up or do we go left? We don't really know. So we need to have a choice between going higher or lower. So that's why we need to start in one of those other corners. Anyway, right, that's filled up that sheet. Only 2 more bits to go. Consider an m by n table, say A, which might not be sorted. An example is shown below. Obtain table B from A by rearranging the entries in each row so that they are in sorted order. Then obtain table C by rearranging the entries in each column. All right, I just want us to fill this in. Okay, so we do the rows first. So we're going to get 24, 33, 46, 92, 8, 25, 26, 37. I mean, this is just 3 marks. This is 22, 40, 49, 81. And then we do the columns. So 8, 22, 24. Then 25, 33, 40. 26, 46, 49. 37, 81, 92. Okay. Show that for any m by n table A, performing the 2 operations from part 3 results in a sorted table C. Okay, so we need to do this for any table. So this is completely generalized for any m by n table. And we're performing those 2 operations. We're going to B, then we're going to C. Well, it feels as though the step from A to B isn't particularly controversial. It's going to be justifying why B to C is necessarily going to work. That seems to be where the interesting part is on all of this. We want to generalize this for any table. That's going to be interesting. So just wondering, so when we're doing the sort, I'm trying to think about how the sort would actually work. If you're arranging things from high to low, if we could make the sort an iterative process, then we just have to show that any kind of higher than, lower than is preserved through each iteration. So what I'm getting at on this is, right, so after, let's try writing some of this out, see if it works. After A to B, then we will have some kind of setup where we've got A, B, C, D going on forever. These are our values in column 1. In column 2, well, just so I don't mix up letters, let's just duplicate these. A, B, B, C, C, D, D. And then so on in each direction in rows and columns. And what we're saying is that we've got all of these inequalities. So that's what we've got. That's just a statement of fact of what happens after we've gone from A to B. So the sort procedure is, as we go from B to C, we could say that we were looking at just flipping terms. Like say we were doing some kind of bubble sort on this or something like that. I don't know. Yeah, but some one term comparison at a time. So let's consider B to C as being an iterative sorting process, comparing neighboring cells. So therefore we can focus on one set of 2 by 2 cells. Right, so what we're doing is we're taking something like, so e.g. A, B, A, B, B. So let's say we were going to sort that little bit, because we can do this over and over again when we're actually doing the step from B to C. It's still going to be sorting them high to low. It's still going to work out fine. So we can say we've got 4 outcomes. So we've got that A is less than B and AA is less than BB, i.e. no change. So in this case, inequalities hold. Inequalities hold. So that would be fine. We've got that A is greater than B and AA is greater than BB, as in we're just flipping both. So flip both columns, which means again we've got inequalities hold. So that is still fine. Then right, I've got all this space up the top here. I use these for the other two outcomes. So we'd have A is greater than B and AA is less than BB. So this is where we'd be moving to B, A, AA, BB. So if we've got that AA was greater than A and B is smaller than A, so that must still hold. And BB, this is the more interesting one. So BB is greater than AA and AA was greater than A. So that will still hold as well. So, and this is because, so what are we saying? We're saying that, what are we saying? We're saying that BB is greater than, which way round am I doing this? Yeah, so on this is because, yeah, BB is greater than AA is greater than A. We had that, so that's why the second one holds. And then we've got that, what was the other one? BB, actually it's exactly the same thing as this, isn't it? So we've got BB is greater than AA and it's greater than B. Well, no, actually, no, we're just in the same position. Yeah, I can say that BB is greater than A is greater than B. So that's going to work, isn't it? For AA, I've just written out the same thing there. Does that make AA greater than B? Yes. So if BB is, oh no, it doesn't necessarily, does it? Sure, I had this just a moment ago, and now I seem to have got myself confused. Right, let's undo these bits. Right, so that's definitely covered the second part. BB is greater than AA, and AA was greater than A. So we had that before. Now we need to show that AA is greater than B. So why would that necessarily be the case if we flip those over? If AA, well, B is less than A. Yeah, that's what I'm getting at, isn't it? B is less than A. So if AA is greater than A, and A is greater than B. Right, so that works. Right, so yes, I've just got myself in a bit of a tangle on that one. So yeah, if we flipped over the A and the B, then BB is greater than AA, and AA is greater than A, so that certainly works for the second inequality. And AA was greater than A originally, and A is greater than B. So yes, that works for the second inequality. So the inequalities hold again. After slightly butchering that one. So that's still fine. And now we need the fourth option. So that's our third option. So we've done 1, 2, that one there, and then fourth option. So that is A is less than B, and AA is greater than BB. So this is taking us to AB, BB, AA. So we need to show that those things still hold. So if BB was greater than, BB is greater than B, which is greater than A, so that one holds for the top one. And then for the second one, we had that BB is, well, AA is greater than BB, which is greater than B. Right, so again, the inequalities hold. So we can, so that's quite a lot, but anyway, we're wrapping this up then with a therefore can repeat these steps for each column to complete B to C. Yeah, okay, that's fine. That's quite a lot to go through there, but I mean, this is something that I was kind of dredging my memory on. This is something that I remember doing in distant past, not this particular question, but in terms of sorting algorithms, it comes up quite a lot when you get various problems at work and such like, where you've got to sort a whole load of data, and you're trying to go through, well, what's the best sorting algorithm to actually use, and you get these comparisons just flipping over neighbouring values. So it was something that was sort of lurking in my memory somewhere, which is why I jumped on that method as a way to go for it. But yeah, that's certainly going to be fine, providing you never break any of those inequalities that you set up. You know, we've got these inequalities going on potentially indefinitely off to the right here as we're moving across the rows, just making sure that they don't break when we're flipping cells in particular columns. Okay, this is a long iterative process, but it's the sort of thing that you'd loop through if you were going to be coding this up. It's one way of sorting that table, of doing that step from B to C. You just need to make sure the inequalities never break, and then you end up with a sorted table. So yeah, that last part was quite tricky, considering, well, part 3 was a gimme, and the first 2 parts of the question weren't that bad, really. So, I mean, I wouldn't say this was a trivial one. There have been easier questions than this when it comes to a question 6. But overall, they were mainly saving it up for part 4. But there you go. That's question 6.